The synchronous motor is similar to the induction motor, with one important difference. The rotor in the synchronous motor rotates at exactly the speed of the rotating field. There is no slip. Put another way, the speed of the synchronous motor is always an exact multiple of the line frequency. This feature is extremely desirable in industrial applications. For example, when several motors along a conveyor belt must all be going at exactly the same speed. Although many synchronous motors are large, the concept is also used extensively in small clock or timing motors, where an exact relationship must exist between frequency and speed. Recall that the rotor in an induction motor receives the power through induction, which requires a difference or slip between the speed of the rotor and the rotating field. To make a synchronous motor work, the power to form a magnetic field in the rotor must come from another source. Traditionally, this is done by supplying DC power into the rotor via slip rings and brushes. Slip rings and brushes on the synchronous motor are similar to the commutator assembly used in DC motors, with one important difference. Here, the electrical contact from the stator to rotor is made through a smooth ring and not the multiple contacts of the DC motor's commutator. The action is smoother, the components last longer, and less electrical noise is generated. The rotor of the synchronous motor uses DC power, called excitation, to energize electromagnets around its perimeter. These magnets tend to lock onto the rotating magnetic field in the stator and cause the rotor to rotate at the exact speed of the rotating field, that is, the synchronous speed. Unfortunately, the synchronous motor is not self-starting. When the power is switched on, the field starts to rotate full speed, causing the magnetized rotor to be tugged first in one direction and then the other. Experiencing no sustained torque, the rotor just sits there. To start the motor, additional hardware is required. Any one of the following methods can be used. 1. Provide for the frequency to start slow and then speed up. As long as the rotating field does not get too far ahead of the rotor will continue to be tugged in one direction. The problem is that it takes extra electronics to provide the variable frequency. However, the advantage of this system is that if you can control the frequency, you can control the speed. This approach is being used more and more with the continuing advancement of high-power solid-state electronics. Another method is to use another motor called a pony motor to bring the synchronous motor up to speed. This approach has the obvious drawback of requiring significant additional hardware. A third method is to insert some squirrel cage rotor bars, as used in induction motors, in the rotor of the synchronous motor. This allows the motor to get started as if it were an induction motor. And finally, use hysteresis synchronous motors, which will be covered later in the chapter. The AC power from the power company arrives with the voltage and current in phase with each other. This is the most efficient way to transmit power because, by definition, power is the product of voltage times current. Therefore, for maximum power transfer, the voltage and the current must be occurring at the same time, that is, in phase. The windings of an induction motor present an inductive type load to the power line. If there are many motors in a facility, the inductive load can be significant. The problem is that the inductive load causes the current to lag behind the voltage, which means the motor will draw more current to deliver the same power. This situation is described in terms of the power factor. The power factor is the cosine of the angle between the voltage and the current. So when the voltage and the current are exactly in phase, the power factor is 1, or unity. For a purely reactive load of a 90-degree phase shift between voltage and current, the power factor is 0. We say that an inductive load creates a lagging power factor and a capacitive load creates a leading power factor. Plant engineers would like to keep the power factor as close to 1 as possible, but how can this be done with a plant full of inductive motors? First, it helps to have the induction motors running with a full load. A lightly loaded induction motor is much more inductive than a fully loaded one. Beyond that, the way to improve a lagging power factor is to add a capacitive load to cancel out all the parts of the inductive load. There are two ways to implement this. One way is to connect large power factor corrective capacitors across the lines, and the second way, surprisingly, is to make use of a synchronous motor. With proper adjustments to the rotor excitation, the synchronous motor will present a capacitive load which will increase the power factor of the plant. Synchronous motors installed specifically for power factor correction are called synchronous condensers. They do not drive a load, they simply spin. Small synchronous motors are used as timing or clock motors, or simply as a source of rotary power in instruments and small machines. They are available to be used as a direct drive or with an attached gear train. Many of these motors are split-phase motors designed to operate on single-phase AC with the use of a capacitor. The simple switching arrangement shown allows for the motor to rotate in either direction. When the switch is in the up position, winding 1 gets the line voltage and winding 2 is phase shifted through the capacitor. This arrangement causes the motor to turn in one direction. When the switch is in the middle position, the motor is off. When the switch is in the down position, winding 2 gets the line voltage and winding 1 is driven through the capacitor. This causes the motor to turn in the other direction. Small synchronous motors do not use electromagnets in their rotors, and so do not need slip rings. Instead, the rotor is magnetized in other ways. There are 3 designs: the reluctance motor, the hysteresis motor, and the permanent magnet motor. All 3 types can be made to be self-starting. The universal motor is so named because it can be powered with either AC or DC. Basically, it is a series-wound DC motor that has been specifically designed to operate on AC. Like its DC counterpart, it is reversible by changing the polarity of either the field or the rotor windings, but not both. Physically, the universal motor is similar to a DC motor, except that more attention is paid to using laminations, thin sheets of lacquered metal, for the metal parts to reduce AC eddy currents, and the inductance of their windings is minimized as much as possible. The operating characteristics of the universal motor are similar to those of the DC motor. For a fixed voltage, the speed is inversely proportional to the load torque. As the load increases, the speed decreases. For a constant load, as the applied voltage is increased, the speed will increase. Typically, universal motors are designed to operate at high speeds, from 3,600 to 20,000 RPM, but because they use a commutator and brushes, which wear out, they have limited life. Being a series-wound motor, they have high starting torque, and for this reason are widely used for handheld power tools, for example, a hand drill motor.